Welcome back to Electron Devices and Circuits lecture video series of which is the part 3 of the topic PN junction diode structure, operation and characteristics. At the end of the video, you will be able to understand the temperature effects in PN junction diode, and also you can able to solve the problem using diode current equation. Let's go into the topic one by one. The first is the temperature effects in PN junction diode. So normally when you look into PN diode, there are two types of charge carriers. One is majority charge carriers and another one is minority charge carriers. With respect to temperature, majority charge carriers does not have any effects, whereas minority charge carriers concentrations changes abruptly with respect to increase or decrease in temperature. So keep this in mind. So temperature affects only minority charge carriers. So keep this in mind and we will see the effects here. So effect number one is cut-in voltage decreases as temperature increases. If we increase the temperature, the cut-in voltage starts to decrease. So this can be observed with respect to this characteristics. So see the characteristics here. So here we have considered the two characteristics. So one is the solid line red color with which represents the characteristics at a temperature of solid line at a temperature of 25 degrees centigrade, and dotted line represents the temperature at 75 degrees centigrade. When you consider the cut-in voltage or knee voltage for the temperature of 25 degrees centigrade, so this is the cut-in voltage at low temperature. Similarly, when we consider the high temperature 75 degrees centigrade, the cut-in voltage is very less. So this much will be the cut-in voltage. So cut-in we can say at higher temperature the cut-in voltage decreases. So this is practically observed characteristics. So the first point is clear, and second effect is I0 increases as temperature increases. So as I already informed, temperature is having major effect with respect to minority carriers. So as we know that, so in the reverse bias condition, the current flowing through the diode is only due to minority charge carriers. So that current is represented as I0. It is also called reverse saturation current or leakage current. So this is the I0 here. So this I0 increases as temperature increases. So when you look into this curve, this is the lower temperature. For lower temperature, this much will be the I0. I0 is present here. So we can say this is the I0. This range is the I0. Similarly, when you are considering the higher temperature, I0 is with reference to this extreme. So at this point you are having the I0. So I0 is this extent. So this is the range of I0 at a temperature of 75 degrees centigrade. So when you look at this current I0, which is higher for 25 degrees centigrade or for 75 degrees centigrade, which is higher? Yes, 75 degrees centigrade I0 is higher. So we can say I0 increases as the temperature increases. So how much it will get increased? That is given by 7% for per degree rise in temperature in case of silicon. If the diode is made of silicon, we can say for 1 degree rise in temperature, I0 increased by 7% of total current. Whereas in case of germanium, we can say I0 increases by 11%. Leakage, that's why I am telling in germanium leakage current is very high. That is one of the reason we are not preferring germanium for almost all semiconductor device manufacturing. So here this indicates, so as the I0 increases, so what happens to this I? What is the conclusion for I? I indicates I decreases. If I0 increases, why I is decreasing? Why I is decreasing? This is with respect to the diode current equation. Current equation, what do you know? I is equal to I0 into E bracket, open the bracket, e to the power V divided by eta V suffix t minus 1. This is the diode current equation. In this equation, if I naught decreases, right, we can say this, when you bring this multiplicative term to the denominator, we can say that if I naught decreases, what happens? If I naught increases, I decreases. That is the reason why I is decreasing here. And again here, so one more thing is I naught 2. What is the current I naught at a temperature? That is a different temperature. We are considering two temperature, 25 degree and 75 degree centigrade. And here I naught 1 is considered as I naught at T1 degree centigrade. I naught 2 is I naught at T2 degree centigrade, and relation between I naught 1 and I naught 2 is given by this expression, where del T is the temperature difference we have considered. So we have considered two different temperatures, so we have to take temperature difference, higher temperature minus lower temperature, 75 minus 25 here. Right. So the third effect is if Vt increases as temperature increases. This is because Vt increases as temperature increases. You know the formula, Vt is equal to K into T, where K is the Boltzmann constant, T is the temperature. If T increases, since this is simply a constant, Vt directly proportional to T. If T increases, Vt also increases. And the fourth effect is VBR increases as temperature increases. So this is evident from this characteristics, reverse characteristics. See here, for a graph of 25 degrees centigrade, breakdown voltage is only up to this range. For a graph of 75 degrees centigrade, breakdown voltage is up to this range. So we can say if temperature increases, breakdown voltage also increases. So these are all the effects. Right. So we have, if we should not have all these effects, we have to use the device. Normally we are using a device in a room temperature only. Suppose if this diode is meant for practical applications at some higher temperature, means minority charge carriers should also be taken into consideration. So that is one important point, you have to keep it in mind. Right. So these are all the four effects. And the next one is how to solve the problems using diode current equation. For sample, I have given here two examples. So rest of the problems you refer the material what I am going to given for you. Right. So first example, the voltage across silicon diode at a room temperature of 300 degree Kelvin is 0.71 voltage. Right. So temperature is given. So for the given data, we have written temperature T equal to 300 degree Kelvin, voltage Vt. Why I am representing this as voltage Vt, this is constant, no, that's why I am taking as it is. So and V is given 0.71 volt, V is 0.71. When 2.5 milliamps current flows through it. So this is the temperature and this is the voltage, when this is the current flowing through it. So current I equal to 2.5 milliamps. So convert it into amperes into 10 power minus 3, you will get this value. If the voltage increases to 0.8 volt, calculate the new diode current. Right? Initially the voltage is 0.71. Now the voltage is increased to 0.8. That means what will be the change in the current? That you have to find out. So for this, in the given data, additionally what I have written is Vt. So because Vt is already known, because it is given as additional hint room temperature. So room temperature in diode current equation topic we have discussed. So Vt equal to K into T. K is the Boltzmann constant, it is having some constant value, multiplied by temperature 300 Kelvin. Normally this T should be in Kelvin. Here the temperature itself is given in Kelvin. So you substitute it here 300, you will get approximately 26 millivolts. So this is a constant, keep it as it is. So the required data for the voltage of 0.8 volt, we have to calculate the current. So here it is given as silicon diode. So for silicon diode, the constant eta equal to 2. So we are taking as it is. And diode current equation, I equal to I naught, substitute the values here. I equal to I naught, you keep it as it is, e to the power V. For V, you substitute 0.71 divided by eta. Eta is silicon for 2 into Vt. Vt is 26 millivolts. So this is minus 1. So substitute the current here. When voltage is 0.71, current is 2.5 milliamps. So substitute 2.5 milliamps from this equation. If you solve this equation, you will get the value of I naught is equal to 2.93 into 10 power minus 9 amperes. That is 2.93 nano amperes. Right? So you know how to solve this in expression, right? Exponential power la irundichina how to solve this ni theriyum illaya. So here all these things are constants. All these things are constant. So divide this and simplify to one new number, and you will get exponential of this. Subtract that value from -1. From that you find I naught. So this is the I naught. Why I am calculating I naught means because I naught is not going to change because temperature is remaining constant at 300 degree Kelvin. So I am using the I naught, same I naught for calculating new diode current. So use the same equation I equal to I naught. Now you substitute I naught here as 2.93 and again e to the power v. V is for new v we have to find. So 0.8 divided by 2 into silicon diode only, Vt new value substituted, and from this find the value of current I equal to 14.11 milliamps. Right? So from the first data you find the value of I naught, substitute the value of I naught for the new voltage and find the new current. This is the required value of current. The next problem is, for what voltages will the reverse current in a PN junction silicon diode reaches 80% of its saturation value at room temperature? Right? For what voltage? Voltage is the required data. And will the reverse current in a PN junction silicon diode? Silicon diode means eta equal to 2. Reverse current. Reverse current means it has to be represented as I naught. Reverse current I naught reaches 80% of its saturation value. 80% of its total I naught. So we have to, for what value of the value of voltage reverse current 80% of total reverse current irukku. That is the question. Right? I equal to 80% of I naught. 80% can be written as 0.8 into I naught. Clear? Why negative sign means it is reducing. Total current la irundhu 80% குறைஞ்சிருக்கு. அப்பனா 8 minus. So use the same formula I. So I is nothing but minus 0.8 I naught equal to the same I naught e to the power for what voltage ங்கிறது இருக்கு. நம்ம voltage கண்டுபிடிக்கணும். So V divided by eta silicon diode 2 into Vt 300, same 300. So 26 millivolt constant. So from this equation I naught and I naught will get cancelled, and see here 0.2 equal to, this means when you bring this minus 1 to the left side it becomes plus 1. So 1 minus 0.8 it becomes 0.2 into e to the power. So exponential la irukra value namakku venum. So for that you take log to the base e on both sides. Log to the base e eduthachu. Log to the base e na, that is nothing but ln. So ln of 0.2 equal to log m power n. Idu enna formula la irukna log, this is log as it is, this is m. So log m power n இருந்தா நம்ம எப்படி எழுதுவோம்? It is equal to n log m ன்னு எழுதுவோம். So v by 0.52 into log e base e. So log e base e, log to the base e cancel ஆயிடும். So this is the value. So இதுல இருந்து v கண்டுபிடிக்கணும்னா இதை multiply பண்ணிட்டேன்னா you will get the value as minus 83.69 millivolt. So இங்க என்ன கேக்குறாங்க, எந்த வோல்டேஜ்க்கு ரிவர்ஸ் கரண்ட் 80% of saturation current போகும்னு கேக்குறாங்க. So the answer is minus 83.69 millivolts க்கு it will go. Right? So two problems we have discussed. I hope you will get the concept how to use the diode current equation while solving the problems. For additional examples you refer the material I am posting it in group. Right? Thank you for watching.